Okay, these notes go over tension and static equilibrium. For static equilibrium, this unit, we're only looking at things linearly, and later on in future units, we'll look at things that are also in rotational equilibrium. So you have to think back to what we're doing today. So I'll read these things to you. You should be taking notes as you're listening to this video. The special situation in which the net force on an object turns out to be zero, called static equilibrium, tells you immediately that the object isn't accelerating. So if you're in static equilibrium, that means that the net force is zero. One common analysis question involves finding the equilibrant force, or you could say equilibrant force, given a free body diagram on an object. The equilibrant is a single force vector that you add to the unbalanced forces on an object in order to bring it into static equilibrium. So what it's saying is, if you look at this right here, what it's saying is that you need a force that is going to balance out both of these. Okay, and so if you think about a force that's going to balance out both of these, what you should be thinking is, I need to add these two forces. So if you look at this one, this force plus this force right here, and you look at the resultant, this is the resultant force there, and what the equilibrant force is going to do is it's going to be exactly opposite with the same magnitude. So your equilibrant force would be exactly opposite to it with the exact same magnitude. So it would be 14 newtons. And this one only says northeast there, so this would be southwest if we're going to use that. But oftentimes we want to have an angle that goes along with it too. So we could do that, but for now we'll just say southwest. Okay? So you can see that your equilibrant force is depicted right there with that purple arrow. Okay, so let's actually do one of these and do the math. So it says that a 20 Newton force due north and a 20 Newton force due east act concurrently on an object as shown in the diagram. What concurrently means is they're acting at the same time. What additional force is necessary to bring the object into state of equilibrium? So what it's saying is it's not accelerating. It will be either constant velocity or it will be at rest. So whatever it's doing now is what it will continue doing. So if you want to pause the video, you can pause the video and give this a try. Okay, so let's do this. So we have a force that's going 20 newtons east, and we have a force that's going 20 newtons north. Okay, so your equilibrant force, or your net force right here, that's what that would be. And so what we need for the equilibrant is going to be this force right here. Okay, and that will be whatever magnitude you find for that net force is the magnitude that it will be for this red force right here. So the way that we figure that out is we do 20 squared plus 20 squared equals c squared, and that'll be our equilibrant. So we're going to do 20 squared plus 20 squared. Square root of all that will give me my value. Okay? All right, and what I put that in the calculator, and I end up getting 28.28 newtons. Okay? So that would be my equilibrant force right here, 28.28 newtons. And we could just say that it is southwest. Okay, so that would be my equilibrant. What that means is that force would be applied, and it would put that net force to zero. Okay, so that's the first one. Next one, this chandelier is hanging from two strings. Okay, so there's a chandelier, it's hanging from two strings. And one thing you have to remember is that when it's in static equilibrium, is that your net force in the x direction will be zero, and your net force in the y direction will be equal to zero. Okay, and so you're actually going to do one of these in your station. So there will be one of these where you do it in your station. So when you look at these these strings, the tension, there's a force of tension that acts upwards from both of these strings. We'll call it FTY. I'll call this 1 and this one 2. And then there's actually a force of tension that acts horizontally as well. Okay, so you can see here that these two FTXs will actually have to be equal to each other, because if this is true, the FTFX is equal to 0, you know that those two forces would have to balance each other. But if we're looking at the weight here, we're looking at the vertical forces. So the Fy is really what we're going to be analyzing. So I'm going to make a more simple free body diagram. Okay, so we've got this FT1, and we've got this FT2, and we've got the weight of this down, which would be FG. Okay, so I'm just gonna go ahead and we'll call these y, FTY, FTY. I'm gonna write a very simple equation for this. So I'll say FTY1 plus FTY2 minus FG will equal 0. And this is asking me for weight, and weight is equal to FG. They're the same thing. Okay, so now I know that if the net force is equal to 0, what I can just say is that FTY1 plus FTY2 is going to be equal to FG, which will be my weight. Okay, now I need to think about how can I figure out what this FTY1 is. So if I think about this triangle here, okay, I'm pulling this triangle out here. This is 427 newtons, and this is my FTY1. And it says that this angle here is 62. Okay, so to figure out my FTY, I can see my FTY is my opposite, and this is my hypotenuse, so that's O and H. So to find FTY1, I'm going to end up doing sine of 62 equals FTY over my force of tension, which is the hypotenuse, which is the 427. So to find FTY1, it's going to end up being 427 times sine of 62. Okay, so there's that one. Plus, now let's look at this triangle. So I'll go ahead and pull this triangle. I'll do it down here. Okay, so I've got that, and then that, and that. That's what it looks like. So 270 newtons here. And then this is my FTY2. Okay, and then this angle here is 42. All right, so that's my opposite, and this is my hypotenuse. So we're going to end up using sine again. So I'll go ahead and do it over here. So sine again. So sine of 42 is the angle equals FTY over the tension in that string is 270 newtons. So what I'll do here is I'll do 270 times sine of 42, and that's my FTY2. And we know that that'll all be equal to FG. So then if I put that in my calculator, I'll do 427 times sine of 62 plus 270 times sine of 42, and I add those two together, and I find that the sum of those is 570.7 newtons, and that will give me my weight. Okay, now this is a really great question. It's very similar to station 2 that you're going to be doing in your activity. But one thing you'll notice about station 2 is it asks you for your mass. And so what you're going to end up doing is you see that this is FG. Well, FG we know is equal to mg. So you'll end up, G is going to end up being 10. So you could find the mass of that chandelier too. You'll find the mass of the mass that's hanging from the 2 spring scales. So just keep that in mind. Okay, so there's that one. All right, this next one, it says, what is the tension in the left-hand wire? Left-hand wire. Okay, so I'm going to go ahead and draw some triangles here. So we've got this. You could do the top triangle too. Either will work. So these forces will be my FTX. So that would be the X component of my tension. Then I'll do this in red. This will be my FTY components of my tension. Okay, and so one thing you're going to notice is that, do you see that these two angles are the exact same? When the angles are the exact same, your components of tension are going to be the same as well. And so you're actually going to do, this will be true for station 2 when you do it again, because you'll notice at station 2, those two angles are the same. Hopefully they stay the same. But your tension, when it's the same angle, it will be the exact same. Okay, so again, we know that this is an equilibrium. So let's go ahead and start with our statement of net force. Let's just do the y direction. Okay, net force in the y direction is going to equal 0 newtons. Okay, so with that, let's go ahead and make a simplified free body diagram. You've got FTY up and FTY up. Okay, and then you have FG that acts down from that stoplight. Now, the thing that's cool about this one is that your force of tension is actually going to be the same in each because they've got the same angle. Okay, so what I could say here is that 2 FTY minus FG is going to end up equaling 0 newtons. Now, again, the only reason that this is true is because the angle is the same on these. Okay, now let's think about FTY. So my angle is 78. I'll go ahead and pull this triangle out here. Okay, and what we're trying to find is this FT here. And this is your FTY, and this is your angle. So this will be your adjacent, and this is your hypotenuse. So A and H, you're going to end up using cosine. So if we're trying to write something for that FTY, we're going to do cosine of 78 equals FTY over FT. And so an equation for FTY would be FT cosine of 78 equals FTY. So we can plug that in right here. So we'll do 2 times FT cosine of 78 minus FG will equal 0 newtons. Okay, now FG, we see that it gives us this 35, and we know that FG is equal to mg, so we can take 35 kilograms times 10 meters per second squared, and we can find that FG is 350 newtons. Okay, so now we can do 2 times FT cosine of 78 minus 350 newtons equals 0 newtons. Okay, now I'm going to go ahead and start to solve for FT because it's asking me right here for the tension in the left-hand wire. We'll know that the tension in both of these will be the exact same because it has the same angle. So now I have 2 FT cosine of 78 equals 350 newtons. I'm going to go ahead and make this stuff a little bit smaller so that I have more space. Okay, I just made some stuff smaller. Okay, so now I need to solve for FT. So I'll do 2 FT equals 350 newtons divided by cosine of 78. And then I'm just going to go ahead and divide by 2 again, too, because you can see that that's multiplying there. So then I have that. And what I end up finding is that my force of tension is equal to 841.7 newtons. Okay, so there's that. And if you have any questions, you're welcome to star some things and ask me when you return, or you're welcome to ask one of your classmates. Okay, I'm going to talk about these 3 stations here. So the station 1, you are going to have a meter stick that looks like this, and you're going to have an FG that acts down. And you are going to try to find the FG, which will then help you determine what the mass is. Okay, now with this meter stick, you also must consider FG of the meter stick. Okay, so that's the biggest thing that people forget is that if you do a simplified free body diagram, you have FG from the mass, and then you have FG from the meter stick that are acting down. Okay, so you need to make sure you consider both of those things, and then you have 2 forces of tension that are acting upwards, and you'll use the spring scale to figure those out. Okay, so that's your first station. The second station, it has an angle, and it kind of looks like this. Okay, and there's the little mass that hangs right there, and then you got your spring scales on the side like that. Okay, and you've got angles written in here. Okay, with that, you've got FG that acts down, and you're trying to figure out from that what the mass is. Okay, so you're going to have to use the tension readings that are in these spring scales to try to figure out what that FG will be. Okay, and then station 3 is a very simple one. You've got your spring scale, and you've got a mass that's hanging from that with FG down, and you're going to then try to figure out the mass from that reading on the spring scale. You'll have to think about how that reading compares to your FG. Okay, make sure you work with a partner on this. If you have any questions, please write down your questions, and I'm happy to help you when you return.